Welcome to CE1 Group 11's Integrated Design Project for the semester January 2021. In this presentation, we will be briefly elaborating about each part of the report, which is the Reaction Engineering 1 part, Process Modeling and Simulation part, as well as the Separation Process 2 part. These are the members of our group. And this will be the contents of our presentation for today.
This is the summary of what we have done for Reaction Engineering 1 part. The objectives of Reaction Engineering 1 part is to propose optimum reaction system for the conversion of formie along with optimal operating condition considering economical and technical feasibility, to determine the type of the reactor, catalyst, microorganisms, and the operating conditions used to convert formie to biogas, and also to determine the strategy to maximize the selectivity and yield of biogas and to minimize the site reaction. Last but not least is to determine the sizing of the reactor. The type of the reactor that we propose to be used in our operation of conversion of formie into biogas is the CSTR. Here are some of the assumptions that can be made about the CSTR, which is the composition and temperature are uniform everywhere in the tank, the effluent composition is the same as that in the tank, and also the tank operates at steady state, which means that mass in is equal to mass out. Energy in is also equal to energy out. The catalyst that we propose to be used in our reactor system is the enzyme xylanase. It helps to enhance the hydrolysis step in anaerobic digestion, and it operates optimally at temperature of 50 degrees Celsius at pH range of 4 to 5.5. By enhancing the hydrolysis steps, it helps to increase the concentration of glucose produced. Glucose is a very important reactant intermediate for the subsequent reactions. It also helps to increase the hydrolytic bacteria in the reactor. As for the type of microorganism that will be used, the hydrolysis and acidogenesis stage will use the same bacteria, which is Clostridium species and Bacillus species. For acidogenesis, it will use Clostridium thermoaceticum, and for methanogenesis, it will use Methanosarcina species. The operating conditions for our reactor systems are as follows. All these operating conditions are chosen based on the optimal condition for the catalyst and microorganism and in consideration for the conversion of formie to biogas. This is our reactor separator system for conversion of formie to help better understand how it works. In the first reactor, hydrolysis and acidogenesis will occur, and in the second reactor, acetogenesis and methanogenesis will occur. Our system utilizes a two-stage system which divides the 4 steps into 2 stages, in which we use 2 CSTRs in series. The hydrolysis stage will produce glucose, which is an intermediate reactant for the subsequent reactions. Meanwhile, acidogenesis produces ethanol, carbon dioxide, and acetic acids. Later, acetogenesis and methanogenesis will produce acetic acid, carbon dioxide, hydrogen, and methane as the biogas.
In this part, I'll be explaining on the strategy to maximize the yield and minimize the site reaction. From the report done, I picked out some of the strategies to explain it. Firstly, to maximize the selectivity and to minimize the site reaction, we can control the operating conditions. For instance, by manipulating the temperature and pH level that is suitable for the microorganisms, they can prosper and thus assist in amplifying the reaction. When these microorganisms are in optimal condition, they can work effectively, hence increasing their yield. Next is by introducing the catalyst. The catalyst is a substance that can be added to a reaction to increase the reaction rate without getting consumed in the process. Catalysts typically speed up a reaction by reducing the activation energy or changing the reaction mechanism. In this case, the catalyst chosen is the enzyme xylanase. Xylanase is a hydrolytic enzyme which is very effective in enhancing the hydrolysis step in anaerobic digestion. This enzyme is proven to increase biogas yield by multiple times. To optimize the function of catalyst, the catalyst shall be clean, renewed, and regenerated. It has been stated that in one of the studies from Valera in 2016, She reported that it is expected and approximated to replace and regenerate the catalyst weakly to maximize the selectivity and yield, thus minimizing the production of undesired products. Lastly, a strategy to maximize the selectivity and to minimize the side reaction, what we can do is by supplying excess water. By supplying excess water, maximize the yield and minimize the side reaction. Supplying excess water helps to minimize the occurrence of side reactions. This is because when there is excess water, any reaction that produces water will be minimized due to the Le-Chatelier's principle. Moving on to the next slide, where we have the sizing of the reactor. A stoichiometry table was done in order to determine the volume of the reactors. In CSTR1, the stage carried out was acidogenesis, while in CSTR2, there is two stages carried out, which includes the acetogenesis and methanogenesis. Before continuing with the calculations, a few assumptions has been made for the both reactors. In reactor 1, hydrolysis is assumed to not occur. Thus, the reaction of acidogenesis will be shown in stoichiometry table. In this reaction, water is supplied in excess, thus it is considered as inert. As carbohydrate will be the main component in the reaction, other elements of forme will be considered as inert. Assume 70% conversion of glucose into ethanol, carbon dioxide and acetic acid. In reactor 2, the acetogenesis and methanogenesis reaction is combined to produce the equation that is shown in the report. The reaction is in gas phase, and A, which is the glucose, acts as a limitant reactant. The conversion is assumed to be 70% of glucose and into methane. Lastly, after calculating, the volume for reactor 1 was 280.388 meter cubic, while for CSTR2, which is reactor 2, is 138.07 meter cubic.
Objectives of PMS part for this project are to develop the mathematical models for the reactor proposed, which is CSTR, to stimulate the steady-state reaction process using process simulation software Exponentis, to validate the simulation by comparing with manual calculations using the reaction system from CEB2043, to calculate the deviation error between simulation and manual calculation, to perform the sensitivity analysis by discussing the effect of pressure, temperature and feed flow rate on reactor performance. Few steps to develop modeling equation. First, I need to state the objective and assumptions for the reaction. Secondly, mass balance for CSTR1 and 2. Thirdly, I need to do component balance, and lastly, the energy balance. For mass balance, firstly, I need to do general equation for mass balance, which is the rate of mass equal to the mass enter the system minus the mass flow out from the system. And I need to simplify the equation until I got the rate of height with respect to time. Next, we move on to component balance. Firstly, I need to state the relative reaction rate, which is K. And secondly, I need to arrange the mass flow enter and the mass flow out from the system. So this is the equation. dNi over dt equal to summation of in I minus summation of n out minus the generation. This is the example of component B balance. Negative K1CA1 square equal to the rate law equation. This is the general equation of energy balance. So the energy balance equal to energy inside the system minus energy out of the system plus the rate of heat plus the rate of work done in the system. So energy equal to internal energy plus kinetic energy plus potential energy. We have made some simplification to make our energy balance become simplified. So we have assumed the system is isothermal and it has the same CP, which is the specific heat capacity of the system, and also no work done and heat is done at the system. So the system is basically adiabatic. For validation part, I have compare the calculated and HYSYS concentration of the component. So I have calculated the deviation error, which is percentage error equal to the accepted value minus the measured value over the accepted value or the actual value times with 100 to calculate the deviation error or percentage error. This is the result for the validation part. I have calculated the percentage error for each component between the HYSYS value and the calculated value. So the concentration of the component have some percentage error. However, this reaction is still accepted because there are some mistakes in substituting the value, which is we do not take the largest significant figure to calculate the value of concentration of the component.
Next, by using data from reaction engineering, we are required to stimulate the steady-state reaction process by using Aspen HYSYS simulation software. This is the set of assumptions made in order to simplify the reaction further. We also assume since there are no cellulose and glucose in the HYSYS, we substitute it with dielectric acid and dextrose respectively since they have the same chemical formula. For this reaction, we use 2 units of CSTR. We also assume that there are 4 stages of reaction happen in the reactors, which is hydrolysis, acidogenesis, acetogenesis, and methanogenesis. Each stage has its own rate constant value. After successfully simulating the proposed reaction process using parameters from reaction engineering part, this is the process flow diagram obtained. And since our estimated conversion rate is around 70%, by using trial and error method, the volume of CSTR1 is 1590 meter cube. The volume of CSTR2 is around 49 meter cube. From the simulated reaction, it can be concluded that the proposed reaction can be achieved or reaction happen as predicted in the reaction engineering part. In CSTR1, the mole fraction of hydrogen and methane is 0 because according to the chemical reaction formula, this component is still not formed at the outlet. Meanwhile, at CSTR2 outlet, there is still unconverted feed in the outlet as the proposed conversion is at 70%. So, in the conclusion, the outlet can be summarized as 45% hydrogen, 31% methane, 17% carbon dioxide, 5% water, and 2% of inert material. Next, we also require to perform the sensitivity analysis by discussing the effect of pressure, temperature, and flow rate of the feed on the reactor performance. And one way to do it is by utilizing the case study function built-in the HYSYS software. The proposed condition of the reactor is at 50 degrees Celsius, 90 kilopascals, and 3420 kg per hour as a mass flow rate. An array of independent variables is set up with an appropriate step size to observe its relation with conversion rate. This is the summary of the case study that has been made. First, on the effect of pressure, we found out that as the pressure increases, so does the conversion rate. Secondly, on the effect of temperature, we can conclude that as the temperature of the feed increases, the conversion rate will decrease. And lastly, as the amount of mass flow rate increases, the conversion rate of the reactor also will decrease. Thus, this will reflect the reactor performance, whereas as the conversion increases, so does the efficiency of the reactor.
For separation process 2, we are required to design the most efficient separation techniques for the purification of biogas with consideration of few aspects, which is operational efficiency, safety, maintenance, and cost. We are also required to propose mitigation solutions to challenges that is faced when selecting the processes. At the end of this part, we also have to devise a strategy to maximize the production of purified biogas. It is known that the biogas must be cleaned and upgraded before it is ready to use. This includes the removal of contaminants that are harmful, toxic, and lowers the calorific value of the biogas. In our findings, the contaminants that have to be removed is water vapor and carbon dioxide. According to the process flow diagram, water is removed first using the adsorption process on silica gel. This is because membrane separation process must be done using dry gas. When the stream is passed through the bed, water vapor is then adsorbed on the surface of the silica gel. When the adsorbent bed reaches its capacity, it is then shut off by closing the valve and undergoes regeneration by heating the bed to dry the silica gel. At the same time, another adsorbent bed is used to adsorb water vapor. This process is done alternately. To remove carbon dioxide, membrane separation process is done using hollow fiber membrane with cellulose acetate as its material. Stream containing carbon dioxide is passed through a compressor to increase the pressure of the stream, because pressure difference is the driving force for this separation. As the stream enters the membrane, carbon dioxide will be permeated much faster and creates separation of stream into low-pressure carbon dioxide-rich and high-pressure carbon dioxide-depleted stream. The carbon dioxide is permeated while the methane is retented on the inlet side of the hollow fiber membrane. For the removal of water vapor, adsorption process is chosen because of these aspects. Firstly, the type of separation is chosen to be the chemical drying through adsorption on silica gel because it is a higher efficiency compared to physical drying. The type of adsorbent used is silica gel due to its high removal efficiency, great moisture and adsorption properties at high humidity levels, great pore surface area and good moisture adsorption while being very inexpensive and low cost. The maintenance of adsorbent beds are also reliable and easy to operate, and it only requires periodic regeneration. The costs for adsorption bed are cost efficient and easy to apply. For the removal of carbon dioxide, the separation technique that is chosen is using hollow fiber membrane with cellulose acetate as its material. This is because hollow fiber membrane has a high surface to bulk volume ratio. It also has a high recovery of methane up to 98% purity, and it is simple and environmentally friendly while being very fast to be installed. The type of material chosen is cellulose acetate because it gives excellent mechanical strength while easy to fabricate with low cost. It has a high selective permeation towards carbon dioxide and is inexpensive due to its abundancy. It also has a high physical strength. For the maintenance of the membrane separation process, it only requires small spaces, available in low capacities, and is easy to be maintained while do not need hazardous chemicals. The cost for membrane separation process is also less in terms of the operational and capital investment. And that is all for our video presentation. Thank you.